Good evening from Pakistan. I am Shiraz Aslam. I'm working as a researcher and PhD candidate at the Department of Electrical Engineering, Computer Engineering, and Informatics, Cyprus University of Technology, Cyprus. Today, I am here to present my conference paper entitled Optimizing Multi-Quay Berth Allocation using the Cuckoo search algorithm. So, maritime container terminals are important nodes in the maritime industry, as maritime container terminal play an important role around the globe. Most of the imports and exports around the globe are done with maritime industry. Maritime container terminal has three fundamental areas: seaside area, marshalling yard area, and landside area. Seaside area, you can see here light blue color, which is primarily responsible for loading and unloading of ships. And the central area is known as marshalling yard area. And marshalling yard area is primarily responsible for storing of arriving containers. And the landside area basically connects internal and external transport. For example, loading of goods from outside the port and sometimes from outside to inside the port. Maritime containerized trade is increasing day by day. For example, in 2018, the maritime containerized trade was 8.4 billion tons, which was increased to 11.1 billion tons in 2019. However, lack of efficient berth planning and improper use of resources increase several problems. For example, accidents at the sea, congestion problem, long waiting time before berthing, and delays in vessels departure. So there is an exigent need of efficient techniques, efficient approaches to deal with this increasing demand of maritime industry. So here, let me explain berth allocation problem. Basically, berth allocation problem lies in seaside area. In this study, I am dealing with berth allocation problem, which lies in seaside area. So, allocating available berthing position to arriving ships at the port is known as berth allocation problem. Berth allocation problem. Okay, in this figure, you can see the process of berth allocation problem. For example, if any ship arrives at point A, and if this ship starts working at point B, the difference between point A and B is known as waiting time. And if it starts working at point B and the requested departure time by vessel's company is point C, so the point C, however, the vessel completes its task at point D, the difference between point C and D is delay in departure time. The fundamental objective of this study is to reduce this waiting time and delay in vessel's departure time. So berth allocation problem depends on several objects, ship characteristics, terminal characteristics, several constraints. Ship characteristics include length of vessel, total load on the vessel, total containers on the vessel, etc. And terminal characteristics include berthing layout. It may be discrete berthing layout or continuous berthing layout, depth of berths, etc. And constraints include preferred berthing position, requested departure time, preferred berthing queue, etc. So this is an example of berth allocation problem. During solving berth allocation problem, we will have a data set like this. We must have against each ship expected time of vessel arrival, it is in hours, handling time in hours, ETD expected time of departure, and PBP is preferred berthing position, and the last column shows length of ship, which is in meters. We will implement our proposed algorithm on this data set, and we will have solution like this. So basically here each rectangle represent a ship where y dimension is vessel length, y dimension is vessel length, here is wharf length, and X dimension is processing time or handling time of any vessel. So the fundamental objective of this study is to minimize total service cost for all the arriving vessels. So in this study, we are dealing with a special type of berth allocation problem known as multi-queue berth allocation problem. In single berthing queue, there is only one straight line where a vessel can be berthed according to their length and the position of other vessels. However, in multiple berthing queues, it considers multiple queues, which adds a new dimension to the berth allocation problem, where we need to one more decision variable, which is berthing queue. Usually in single berthing queue, we need two decision, berthing position and berthing time. However, in multiple berthing queue, we need three decision variable, berthing position for each ship, berthing time for each ship, and berthing queue for each ship. You can see here this figure. This is an example of multiple queues. You can see here, this is Q1, this is Q2. There are total 10 ships. Our algorithm assigns any arriving ship based on their lengths and processing time to Q1 or Q2. This work presents a solution to multi-queue berth allocation problem using continuous berthing layout and dynamic vessels arrival. Here is total processing cost for ship S. In our formulation, total processing cost depends on three variables: waiting cost for each ship, handling cost for each ship, and late departure penalty for each ship. You can see here, this is waiting time multiplied by waiting cost. This is handling time multiplied by handling cost. And this is penalty function. And the last one is late departure time multiplied by late departure cost. Here, the waiting time is equal to berthing time for ship S minus expected time of arrival of ship S. This function calculates a penalty against non-optimal queue. For example, if ship one requested for Q2, for example, Q2, if our algorithm assigns Q1 instead of Q2, a specific penalty is added in handling cost because of long distance for storing of containers. If assigned Q is equal to PBQ, PBQ is a preferred berthing queue, penalty is 0. Otherwise, if Q is equal to ABQ, ABQ is alternative berthing queue. So it means the penalty, fixed penalty is added into handling cost. Otherwise, infinite penalty is added. The late departure time for any ship is calculated as the difference between finishing time and requested departure time, where finishing time is equal to berthing time of ship S plus total handling time of ship S. The objective function is to minimize total handling cost, which total weighted cost that includes handling, waiting, and late departure penalty cost. Here are some constraints related to our formulation. This variable is one if ship S is assigned to berthing position B of Q at berthing time T. The second constraint, ensure each ship berths only once during the planning horizon. The third constraints ensure that the proposed berthing time always and must be greater than or equal to expected time of vessel arrival. And the next constraint ensure that the berthing time of ship S, berthing position of ship S plus length of ship S always and must be less than or equal to length of assigned Q. Okay, this constraint guarantees that no two ships overlap each other. You can see in this figure, if a specific position is assigned to ship I, so it means this position cannot be assigned to ship J. So in any case, no two ships overlaps. The last constraints ensure that safety entrance time between two ships, which is considered half hour between two ships. So To solve this problem, we have developed a meta-heuristic based Cuckoo search algorithm. It is an optimization algorithm inspired by the breeding behavior of some cuckoo species by laying their eggs in the nests of other host birds. There are 5 fundamental steps of Cuckoo search algorithm. At step 1, generate initial population of n host nest. Step 2, lay the egg in the K nest, where K nest is randomly selected, and cuckoo's egg is very similar to the host egg. You can see here, okay. Then at the step 3, compare the fitness of cuckoo's egg with the fitness of the host egg. At the step 4, if the fitness of cuckoo egg is better than the host egg, replace the egg in nest K by cuckoo's egg. Otherwise, the host egg is considered. At the step 5, if host bird notices the cuckoo egg, the nest is destroyed and new nest is built to avoid, in order to avoid local optima. There are 3 fundamental rules for cuckoo search algorithm. Each cuckoo lays 1 egg at a time in a randomly chosen nest. The best nest with a high quality eggs will be carried over to the next generation. The egg laid by a cuckoo is discovered by the host bird with a probability of 0 or 1. If the cuckoo egg is discovered by the host nest, the cuckoo egg is destroyed and new one is built. So here is a mapping of cuckoo search algorithm to birth allocation problem. Here you can see each nest demonstrate a solution set which includes birthing time for each sheep, birthing position for each sheep, and birthing queue for each sheep. And a single egg will be either birthing position, or birthing time, or birthing queue. Where cuckoo egg will be a new solution or better solution. It may be birthing time, or birthing position, or birthing queue. The total number of host nests are fixed, which shows total search space. And in our study, we have considered 100 host nests. For experimental setup, we have considered real-time data taken from the port of Limassol, Cyprus. A satellite view of port of Limassol is presented in this figure. You can see here there are total 7 queues at the port of Limassol. However, in our data set, we found five queues, excluding CPA queue and South queue. Other 5 are included in our data set. We have taken a real-time data set from March 2018. And we have performed experiments on first week of March, where we found 28 ships which are arriving in first week of March. We have data like this: ship number, ETA, expected time of arrival, 1 mean day, first date 4 o'clock. HT is handling time in minutes. ETD is expected time of departure. Again, day and time. PBQ is preferred berthing queue, which is also provided by shipping companies. And the last one is length of ship, which is in meters. So I have presented only 10 ships here. However, we have 28 ships arriving in first week of March 2018. As for comparison purpose, we have also implemented 2 benchmark approaches. The first one is popular meta-heuristic based genetic algorithm, and the second one is mathematical solution mixed integer linear programming. So here is a solution developed by 3 different algorithms. You can see here I have presented results in 5 different queues. You can see here Q1, North queue, West queue, East queue, container queue, and container row queue. So this one is a solution proposed by Cuckoo search algorithm. This one is proposed by genetic algorithm. This one is MILP, mixed integer linear programming. Here, each rectangle represent a ship basically, and the number next to the rectangle demonstrate ship number. For example, this is ship number 8, ship number 15, ship number 18, ship number 22, ship number 28. Again, y dimension is vessel length. Y dimension is vessel length as a wharf length, and x dimension is processing time or total service time for loading and unloading of containers. Let me explain further for results. You can see here, this is proposed and requested departure time proposed by 3 different algorithms. Here, blue line shows solution by Cuckoo search algorithm, red line shows by genetic algorithm, green line show by mixed integer linear programming, and black line is requested departure time, which is given by shipping companies. Here, you can see here, all the ships are arriving before requested departure time, except only one ship, ship number 2. Here you can see here, using genetic algorithm, ship 2 is departing late only for 1 hour. 1 hour. Other than this, all the other ships are departing early before requested departure time, even using Cuckoo search algorithm and mixed integer linear programming. So it means using this, there is only one ship departs late using genetic algorithm. On the other hand, when we compare in terms of waiting time, we can see here there is no waiting time using Cuckoo search algorithm and mixed integer linear programming, as mathematical language always provide optimal solution, and here our Cuckoo search algorithm is also providing optimal solution. However, using genetic algorithm, there are around 12 to 13 ships that depart late, and the maximum waiting time is 9 slots, and each slot is equal to 30 minutes time interval. Here is total cost proposed by Cuckoo search algorithm, genetic algorithm, and mixed integer linear programming. You can see here, when we perform experiment for 1 week, the total cost using mixed integer linear programming is 5,385 euro. Same for Cuckoo search algorithm. However, when we use genetic algorithm, the total cost is 6025, which is higher than other 2 algorithms. As for computational time, you can see here mixed integer linear programming is taking highest computational time, which is 910 seconds. On the other hand, genetic algorithm is taking minimum computational time 1.79 seconds. However, our Cuckoo search algorithm is also taking very low computational time, which is 4.49 seconds compared to mixed integer linear programming. As for conclusion, in this study, we focus on multi-queue berth allocation problem using continuous berthing layout and dynamic vessel arrival. Meta-heuristic based Cuckoo search algorithm is developed. As for comparison purpose, genetic algorithm and mixed integer linear programming methods are implemented. The newly developed Cuckoo search algorithm outperforms genetic algorithm in terms of cost, which is 11.2% lower than genetic algorithm. As compared to mixed integer linear programming, our proposed CSA Cuckoo search algorithm provides an optimal solution within a low computational time, which is 200x lower. In the future, we are planning to consider more complex and practical problems formulations. For example, we are planning to consider hybrid berthing layout, handling uncertainties, combined berth allocation problem, and queue crane allocation problem, etc. So thank you very much for your attention.
Yeah, thank